begin, a couple of definitions. Zero-order processes go at a constant rate. The rate doesn't change as the concentration of components of the process change. It's a linear relationship. First-order processes, the rate changes as the concentration of one component in the process changes. It's an exponential relationship. When we talk about elimination, we usually talk about rate of elimination equals amount of drug eliminated from the body per unit of time. For example, milligrams per hour. When we talk about clearance, we talk about a theoretic volume of fluid cleared of drug per unit of time, for example in milliliters per hour. This is because drugs distributed outside of the circulation don't get delivered to the organ of elimination, so a rate limiting factor for most drugs that undergo first order or flow limited elimination, is the rate of delivery to the organ of elimination, and this happens through the circulation. Think about this. As we eliminate the drug from the body, the amount left in circulation diminishes, so the amount delivered to the organ of elimination decreases, so the milligrams per hour elimination decreases per time. For first-order elimination drugs, which is the most common, the fraction of the drug cleared remains the same, despite that the milligrams per hour decreases. For drugs that are capacity limited, the organ of elimination is going as fast as it can, so changes in rate of delivery don't lead to changes in clearance. A set milligram per unit of time can be removed. This is known as zero-order elimination. Some common zero-order substances include ethanol, aspirin at toxic levels, phenytoin, and theophylline. The illustration depicts the concept of extraction ratio, where we compare the amount of drug entering the organ of elimination, usually the liver, compared to the amount exiting the organ back into circulation. A high hepatic extraction ratio, more than 0.8, indicates a high probability of significant first-pass metabolism. Meds taken via the oral route, and to some degree meds given via the rectal route, pass through the liver immediately after absorption into the portal vein. Drugs with high affinity for the metabolizing enzyme will get demolished before they ever hit systemic circulation. This is a first-pass effect or first-pass metabolism. Some drugs are eliminated through addition of a highly water-soluble conjugate such as a glucuronide conjugate. This increased hydrophilicity allows the conjugated drug to be trapped in the urine or in the lumen of the gut. In the lumen of the gut, the microbiota often cleave the conjugate, chewing it up as food, allowing for reabsorption of the drug in a process known as enterohepatic recycling. Fun fact, conjugated bilirubin is glucuronidated bilirubin. Clearance is measured in units of volume of fluid cleared per unit of time. It's a summation of clearance through all routes, hepatic plus renal plus other. Biotransformation, which is metabolic modification of the drug molecule usually done by the liver, is a form of elimination. Elimination equals biotransformation plus excretion. The rate of elimination, milligrams per hour, for most drugs is proportional to the concentration of the drug in the blood. Since the concentration of the drug changes as the drug is eliminated, the rate changes with respect to concentration. In other words, it's dependent upon concentration. This is known again as first-order elimination. It depends on the rate of change of concentration, and you thought calculus was irrelevant, right? When a drug concentration approaches Vmax, the maximum capacity for the enzyme or transporter to clear it, the rate of elimination is constant. This is zero-order elimination. It doesn't matter how quickly you deliver the drug to the eliminating organ, the process is saturated. The plot at the top is a Michaelis-Menten plot of velocity of enzymatic reaction on the y-axis as a function of the substrate concentration. Note that Km is the concentration at which the enzyme is functioning at 50% of maximum velocity, also known as Vmax. When the drug concentrations exceed the Km for the metabolizing enzyme, we begin to transition from first-order elimination to zero-order elimination. The plot at the bottom shows the Lineweaver-Burke double reciprocal plot that transforms a curve on the top into a straight line. Let's talk about the renal elimination rate. Renal elimination equals the amount filtered at the nephron plus the amount secreted into the urine minus the amount reabsorbed from the urine back into the body. Plasma protein-bound drugs generally aren't filtered, but most other drugs filter pretty freely through the fenestrations in the glomerular membrane. Some substances will be actively secreted in the urine, while some will be actively reabsorbed. Highly hydrophilic drugs will not be able to passively diffuse back into circulation, but lipophilic substances can diffuse back into circulation, back into the body. One confusing point sometimes, as urine concentration of a substance increases, blood concentration decreases. A really important term to know is elimination half-life. Elimination half-life, T1 half elim, is the amount of time it takes to eliminate 50% of a drug from the body. For a drug that undergoes first-order elimination, the milligram per hour eliminated changes, but the half-life will remain constant. For drugs that undergo zero-order elimination, the milligram per hour eliminated stays the same, so there is no true elimination half-life. The half-life changes. Zero-order elimination rate does not change as concentration in the blood changes. first order elimination rate changes as the concentration falls due to elimination. The equation that defines the curve has one exponent that ties the rate of change in concentration to the change in concentration. That's the definition of first order. To illustrate the difference between first and zero order kinetics, imagine two buckets with holes in the bottom. Each bucket initially contains 100 milliliters of water. The zero order bucket, blue line, has a fixed hole that will allow 10 milliliters of water to drain per hour. The first order bucket, the gold line, has an elastic bottom that will stretch and contract with the weight of the water so that 10% of the remaining water will drain per hour. For the first order bucket, the gold line, at about hour 7, 50% of the water has drained, from 100 mils to 50 mils. At about hour 14, the volume has reduced by about 50% again, from 50 to 25 milliliters. Thus, the half-life, T1 half, or the amount of time to clear half of the water from this bucket is about 7 hours. There's some distortion in the graph above due to limitations in Windows graphing, so the numbers are approximate. Notice in the zero order bucket, half of the water is gone in 5 hours from 100 mils to 50 mils. Then it takes only 2.5 hours to go from 50 to 25, and 1.25 hours from 25 to 12.5, so there's no true half-life for zero order buckets and drugs that undergo zero order elimination. In zero order kinetics, the rate of elimination is constant and there is no true half-life. Important points for zero order: drugs that undergo zero order kinetics tend to accumulate with repeated dosing. Doubling the dose for repeatedly dosed drugs will cause a disproportionate change in serum concentration, much more than double. In comparison, if we double the repetitive dose of a drug that undergoes first order elimination, the serum concentration will also be doubled. This graph depicts a concentration versus time curve after a single dose of intravenous medication that undergoes first order elimination. How can you tell it's IV? Well, there's no absorptive phase. The Cmax is found at time t equals 0, so Tmax is at the point of administration without any time needed for absorption. If the volume distribution of this drug is 10 liters, number 1, what dose was given? While looking at the graph, we see that our Cmax was 10 milligrams per liter. Using factor labeling, we can see that 10 milligrams per liter times 10 liters leaves us with units of milligram, which is a common unit of dose expression, so our dose was 100 milligrams. Number 2, looking at the graph, what's the elimination half-life of this drug? We go from 10 milligrams per liter to 5 milligrams per liter in 2 hours, then from 5 to 2.5 in 2 hours, so we know it's first order because the half-life is constant and the half-life is 2 hours. Number 3, half-life is important. It takes 4 half-lives to clear 94% of a first-order drug and 5 half-lives to clear 97% of a first-order drug once you stop administering the drug. Half-life is also important because it's dependent on clearance, so you can use half-life to calculate clearance and vice versa. The relationship between half-life and clearance is indirect, since it's actually the elimination rate constant, KEL, that relates to clearance, but we can figure KEL from half-life. Half-lives times KEL equals 0.693. I actually always remember KT 0.693. Clearance equals K elimination times volume distribution. My colleague, Dr. Callie Weaver, always remembered the equation for clearance as clearly Callie multiplies VD. You can also look at units to figure it out. Clearance in milliliters per hour, KEL in reciprocal time, hours to the minus 1, and VD in volume, for example, milliliters. Our clearance is 0.7 divided by 2 hours times 10 liters equals 3.5 liters per hour. In order to maintain a drug concentration above the minimum effective concentration, we'll need to replace what's lost from the body through clearance. For your information, I've posted the equation for this line. Concentration at any time t equals C0 times e to the power of minus KEL times t, where t is a time elapsed between C0 and the concentration at time t. This slide sums up what we just walked through for a single IV first-order elimination drug. Our Tmax was 0, so we can assume that it was given IV. Our Cmax, reading from the graph, 10 milligrams per liter. We can calculate our volume of distribution, dose divided by Cmax. We knew that we gave 100 milligrams. 100 milligrams divided by 10 milligrams per liter. Volume distribution, therefore 10 liters. Our half-life is the time needed to decrease the concentration by half. It's 2 hours consistently, therefore we know it's first order. Our elimination rate constant, KEL, equals 0.693, which I rounded up to 0.7 divided by half-life. So 0.7 divided by 2 is 0.35 reciprocal hours. Clearance, clearly, Callie multiplies VD, so our K elimination, 0.35 reciprocal hours times 10 liter volume of distribution, therefore clearance is 3.5 liters per hour. It will take 10 hours to clear 97% of the drug, 5 half-lives. Let's look at what happens when we keep administering drug, CIVI, continuous IV infusion. At the left, we see the concentration versus time curve for a single dose if the drug is given by IV bolus, while at right, we see what happens when we give the drug by CIVI. As we infuse a drug that undergoes first-order elimination at a steady rate, we eventually get to the point where the rate of infusion of the drug in equals the rate of the drug out. This is known as steady state. Rate in equals rate out. The final steady state concentration will be equal to the rate of the drug infusion in milligrams per hour divided by the clearance in liters per hour to equal concentration milligrams per liter. The time needed to achieve steady state is determined by the elimination rate. The final concentration at steady state is determined by the rate in. So once again, rate out determines the time needed to achieve steady state. Rate in determines the concentration at steady state. It takes about 4 to 5 elimination half-lives to achieve steady state because remember, the time needed for steady state determined by elimination rate or rate out. On this slide, we're comparing repeated intermittent IV doses. On the left, the dose is repeated more frequently than 5 half-lives, so the drug accumulates until steady state, rate in equals rate out. On the right, we see that the drug doesn't accumulate if the dosing interval tau is longer than 5 half-lives. Plasma drug concentration at steady state is going to depend upon the rate of infusion, the rate in, while the time it takes to achieve steady state depends on elimination rate, the rate out. And remember, steady state is defined as rate in equals rate out. This slide is here to provide a visual to explain the 5 half-lives to steady state concept. This time our magic bucket drains 50% of the water contained in the bucket each hour. We're adding 100 milliliters of water every hour. After adding 100 milliliters at time 0, we have 50 milliliters left after 1 hour. So we add another 100 mils to total 150 mils. At the end of the next hour, we have 75 milliliters left, etc. You see that at the 5th half-life, we're draining almost 100 milliliters, which is the amount we're adding, so the rate in essentially equals the rate out. What's the K of elimination for this bucket? We're draining 50% per hour, so our half-life is 1 hour. 0.7 divided by half-life equals KEL equals 0.7 reciprocal hours.